regarding bonus quiz 2. With the previously posted edition of bonus quiz 2, I did not supply all the details necessary for question 1. I fixed it. So please get the modified version of bonus quiz 2 from Sakai. And because of this goof on my part, we'll extend the due date by a day. I don't think I changed the due date on the bonus quiz. You can scribble that in. Now, more on deriving half reactions. In particular,
is that totally this Saturday?
Yeah, today's the 10th.
Yeah.
So I don't even get dates right these days. All right. 10, 17, we'll make it 16. That's Tuesday next week, is it not? Yay! I got that part right. Chemistry's okay. This kind of stuff throws me for a loop. I've been suggesting for a good long time that the world adopts the Horvath calendar. Very simple. Instead of 12 months, we have 13 months. Each month is 28 days. Each leap year, we have 2 January 1st. We can have double the football games. Or if you prefer, 2 December 28ths. So you can have 2 New Year's Eves. I don't care. And this way, we make one calendar and it never changes. Every year starts on a Sunday. Every January 1 will be a Sunday. How simple it could be. And the last day of every month will always be a Saturday.
What do we call it, 13th?
13th, we'll call it Horvathium. How's that? I don't care what you call it. But I really resent the amount of time I have to spend every year, particularly in fall, designing a calendar for operation of the teaching lab. This is nonsense. Which days of the week do Labor Day make up? Which days of the week do Veterans Day make up? Which days of the week do Homecoming make up? All this stuff changing all the time. And when we get fall terms that start so that the first day of laboratory is Labor Day, that really causes more fun. All this stuff. Just because of this goofy calendar. Just because of the idiots who administrate this university have not yet realized you should never start school on a Wednesday. That's not the way to do it, but that's the way they're doing it again this fall. All school should start Monday and all classes should end Friday. This reading day stuff is more baloney. Political nonsense. I asked about it. Explanation I received is this would put a stop to faculty who insisted on giving final exams before the final exam period actually began. Baloney! Her faculty giving final exams whenever they want all over this campus. That hasn't stopped anything except cut 2 days off the damn term, which threw away the entire last week of laboratory. People that do this are so stupid. They never pay attention to the folks in the trenches. Never. They sit there and count days. That's all they do. Doesn't matter. In any case, I'm sure my idea on operation of the school calendar will have as much impact as my Horvath calendar idea. But I'd like it. Make one calendar, it lasts forever. The only thing that's going to change is the year. Nothing else will change. Every Sunday's the same date. Every Tuesday, every month, same date, every year. So nice, so simple. Calendar makers might hate me. I don't give a damn. We want to make this life as straightforward to live and get on with the things that are important, like education, not fooling around with calendars. That's not important, in my humble opinion, which I'm sure you've realized is anything but humble. But we proceed. Deriving half reactions, the real nuts and bolts of electrochemistry. As we have been doing all term with acid-base chemistry and semi-soluble salt chemistry. Hey, if you want to know what's going on in the system, a system in which a reaction takes place, you have to be able to write the correct equation for the reaction. So first and foremost is always PSI. You cannot escape from this simple reality. If you don't know what the heck the system is composed of initially, you have no chance whatsoever to understand the chemistry which will occur, or at least can occur, in the system. Same theme, different category of reaction, but same theme. Now, based on where we finished yesterday, in regard to deriving half reactions, an illustration of the rules of the road for such. There are considerations given. I guess I could give you a page reference, page 2213. That's where this stuff is from. On the oxidation of chloride ion to chlorate ion. That's the name for this. I don't care about its name. If you just write its formula, ClO3-, that's fine. First in 1 molar sodium hydroxide solution, second in 1 molar ammonia solution. The reaction equations are different. Why are they different? Because in one system, hydroxide ion is the principal oxygen atom containing species, or the principal species from which oxygen atoms will be derived. But in the second system, the ammonia system, water molecules will be the species from which oxygen atoms are principally derived. Because clearly, if I'm going to convert chloride ion to chlorate ion, I've got to add -2 oxidation state oxygens to chloride ion in order to do this. In this case, I'm making covalent bonds. Remember when we looked at nitrate ion going to NO? There we were breaking covalent bonds from the central atom nitrogen to oxygen. Here we're going to make covalent bonds involving oxygen to what will become the central atom chlorine in this chlorate ion. So here's the two reaction equations. We need to tear apart 3 hydroxide ions to give us the 3 -2 oxidation state oxygens. Call them oxide ions if you will. Which then covalently connect to chloride ion to make chlorate ion. Why 6 hydroxide ions? Hey, when we tear apart these 3 hydroxide ions, beside making -2 oxidation state oxygens, we're making +1 oxidation state hydrogens, H+. And what's always going to consume H+ in any system? The strongest base present in high concentration or amount in the system. So in the hydroxide ion solution, that's hydroxide ion. So 3 of these to give us the oxide ions and 3 more to eat up the H+. But in ammonia, now the strongest base is ammonia, and again the best oxygen atom source is water. So I got to tear up 3 water molecules. This puts 6 H+ into the pot. And in the ammonia solution, what will catch the H+? Same game. Strongest base present in high concentration or amount, which is now ammonia. So here, in addition to making chlorate ion, we're making ammonium ions. Now we go to question 2215. Again, many of you have had a look at this. But we'll take another look, because this is important stuff. And it's all about learning how to derive equations for half reactions, which after you have them, if it's necessary to write the equation for the net redox reaction, you couple the half reactions, you get the net redox reaction. That's what's going on. And in addition to PSI, this. If you've been working at this stuff, you see these redox reactions very often involve acid-base chemistry, often involve the formation or the reaction of a salt of limited water solubility, or, as we've also recognized, complex ions, which we've talked about in brief at the end of chapter 19. So this stuff is all building on chemistry which we have labored to get at in previous chapters. First part of 2250, oxidizing silver in 6 molar nitric acid solution. You can look at the parts in the notes. So in this case, we're making silver ion. Now silver ion forms a defined hydrate. Its formula is this. It's a dihydrate rather than a hexahydrate. But I don't mind leaving off the water molecules in making silver ion AQ because the acid strength of this is so feeble that practically speaking the presence of this in water has little if any effect on pH. So we'll take this liberty here. You can't do that with hydrated copper ion. 1 molar hydrated copper ion shows a solution pH of about 4. How many of you in 46L did this in assignment 6? Right. So you can neglect the waters of hydration on copper ion in solution, or magnesium ion in solution, or aluminum ion in solution, or iron +3 in solution. Metal ions which have much greater positive charge densities than Ag+. And when we oxidize copper with nitric acid solution, the reduction product was NO. Here, same reduction product. So nitrate ion will be reduced to NO, and as we recognized yesterday, this half reaction contains also what? Remember this? Breaks NO bonds, puts -2 oxidation state oxygens into the pot, call them oxide ions. Oxide ions react with the strongest acid present in high concentration. In nitric acid solution, that's hydronium ion. So you got hydronium ions here as reactants and water molecules as products. We did this. This half reaction in its entirety is in the short list half reaction table which we finished developing yesterday. Part 2. Now let's talk about oxidizing silver in aqua regia. Did you read this stuff regarding question 2250? Aqua regia. Water of royalty. An interesting term. What's the significance? The historical as well as chemical significance of this term aqua regia. Any idea?
It's a potent oxidizer, and to the point of it can actually oxidize some very unreactive metals such as gold and platinum, which is royal.
What do you know about metals like gold, platinum, palladium? Maybe you don't know much about palladium, but I'm sure you know about gold, silver. These are very valuable metals. Now, in all honesty, I don't know why these are very valuable. From a utilitarian standpoint, iron is a heck of a lot more valuable than gold will ever be. But what do we got in Fort Knox? Another illustration of the idiocy of humankind. That's my opinion. a bunch of gold bars upon which we place great value. A metal which, practically speaking, has very little usefulness. What's going on here? It's rare stuff. Well, hell, there are no two snowflakes alike. Why don't we preserve snowflakes? Well, they don't have the ability to stay around a long time like gold does. But so be it. Aqua Regia has the capacity to dissolve these valuable yet very unreactive metals. Gold, platinum, palladium. Straight hydronium ion alone won't do anything to gold. Like it won't do anything to copper. Like it won't do anything to silver. Like it won't do anything to platinum or palladium. You need another boost in here. Now, in Aqua Regia, beside hydronium ion at high concentration, you also have nitrate ion. We found that nitrate ion, along with hydronium ion, can oxidize copper. This tells us that nitrate ion, along with hydronium ion, can oxidize silver. Won't oxidize gold. You need the other component in Aqua Regia to oxidize gold. That's chloride ion. Because now we're going to form a complex ion. So you need not only strong oxidizer attack, you need complex ion attack. Or a complexer attack to make a complex ion. That's where Aqua Regia gets its name. Not so much concerned about the history, but what does matter is to recognize, as we must always do, PSI for Aqua Regia. Because with chloride ion in there, when we oxidize silver, we're not going to make silver ion AQ. Instead, we're going to make silver chloride. So look at these two. If I oxidize silver in Aqua Regia, why do I make silver chloride instead of silver ion AQ? Got the half reaction table? Look at it. Again, we need to let this information talk to us. You will see in the table that the half reactions to which we are referring, the oxidation of silver to silver ion AQ, and the oxidation of silver in the presence of chloride ion to make silver chloride. These half reactions are right next to each other in the table, aren't they? Which one is thermodynamically more favorable? Silver to silver ion or silver to silver chloride? Silver to silver chloride, a good deal more favorable. Each of these half reactions have a negative electrochemical potential. But the negative potential for silver becoming silver chloride is minus 0.22, if my memory's right. Whereas turning silver into silver ion AQ is minus 0.8. That's a lot less favorable. So, again, this half reaction table is a table that's loaded with thermodynamic stability information. We make this rather than this, because this is a lot more stable. Enough said. 3. Again, we're going to oxidize zinc to make hydrated zinc ion, like we did in the redox demo. Except in the redox demo, we oxidize zinc in sulfuric acid solution. Now we're going to oxidize zinc in 6 molar nitric acid solution, but we'll still make hydrated zinc ion. But this time, with nitrate ion again being the species that gets reduced, we don't get NO, instead we get nitrogen. So on the basis of silver being oxidized in nitric acid solution, copper being oxidized in nitric acid solution 6 molar to make NO, when we oxidize zinc in 6 molar nitric acid solution, we make nitrogen. What is the difference in these two redox products? NO versus nitrogen. What's the difference in these redox products tell you about the reducing strength of zinc versus silver or copper? Now, we already know zinc is a stronger reducer than copper. That came from our redox demo. It came from the zinc ion copper ion cell we considered. Now we got more information which keeps with this. Zinc reduces nitrate ion, we get nitrogen. Copper reduces nitrate ion, we get NO. How does this keep with the fact that zinc is a stronger reducer than copper? What do you say about this? How can you interpret this information to support the conclusion that zinc is a stronger reducer than copper or silver? This is what we're talking about. There's all kind of stuff like this on exam number 3. Any comments? Nitrate ion. Oxidation state of nitrogen +5. NO, oxidation state of nitrogen +2. Oxidation state of nitrogen in nitrogen molecule 0. Hey! We produced a much greater change in the oxidation state of the species that got reduced by reducing that species with a stronger reducer. Mg. In 6 molar nitrate. Now you pursued this matter, the matter I'm going to ask about. 2045 lab, assignment 5, part 1. Which is the stronger reducer, magnesium or zinc? Magnesium or zinc? What's the stronger reducer between these two? If you didn't know, but I let you go to the laboratory to do experiments to answer this question, what experiments would you do? Two metals. What will you do to find out which of these metals is the stronger reducer? What are you going to do? What did we do to resolve this question between copper and zinc? Strip of copper, zinc sulfate solution. Strip of zinc in copper sulfate solution. In which of these systems did we get a reaction? Copper and zinc sulfate solution, nothing. Zinc and copper sulfate solution, immediately copper metal starts to form on the surface of zinc. As zinc gets oxidized to zinc ion. Hydrated zinc ion. Same idea here. Take solutions which have the same anion. Sulfate ion, nitrate ion, who cares? Zinc in a solution of magnesium ion. Hydrated magnesium ion, a hexahydrate. Magnesium strip in a solution of hydrated zinc ion. That's what you do. Because in one of these systems, you're guaranteed to get a redox reaction. If magnesium is a stronger reducer than zinc, when you put the magnesium in contact with hydrated zinc ion, immediately zinc atoms will start to form on magnesium as magnesium is oxidized. Or, if zinc is a stronger reducer than magnesium, then in the system with the zinc strip in contact with hydrated magnesium ion, immediately magnesium will begin to form on the surface of zinc as zinc is oxidized to hydrated zinc ion. You did this in 45 Lab. Anybody remember the result? Anybody remember which of these metals is the stronger reducer? You learned about stuff like this in 2045, but not by the direct experiment fashion. In 2045, did you not learn that these 1A metals are the most reactive metals? How about the 2A metals? Remember, the 1A metals are called alkali metals. The 2A metals are called alkaline earths. Did you hear this language? How does the reactivity of the 2A metals compare in general to all the other metals? The 2A metals versus all the other metals. 2A metals are more reactive, less reactive, or about the same? More reactive. You betcha. 1A metals are the most reactive. The 2A metals are the second most reactive. Not as reactive as the 1As, but generally more reactive than all the other metals. Well, that gives you a clue on this, doesn't it? Supports the conclusion that magnesium is a stronger reducer than zinc. Well, let's give you a piece of information. If I oxidize magnesium with 6 molar nitric acid solution, the reduction product is this. Ammonium ion AQ. What's the oxidation state of nitrogen in ammonium ion? What is it? What is it?
It's a -3.
-3. Hey, with this more potent reducer, I take +5 nitrogen and nitrate ion and clobber it all the way down to -3 oxidation state nitrogen in the ammonium ion, which happens to be the lowest oxidation state nitrogen atom can ever have. You learn about stuff like that in 2045 too, because nitrogen is an atomic member of family 5A. You learn the significance of this 5? Didn't? 5 valence electrons. When nitrogen becomes -3 oxidation state nitrogen, what kind of electron configuration does nitrogen now have?
Noble gas.
How about that? Noble gas. So that's where the chemistry stops. Now nitrogen with 5 valence electrons. This is more 2045 stuff. Nitrogen can also convert to noble gas structure, be isoelectronic with helium, if it loses all 5 valence electrons. What do you think is cheaper and easier to do? Collect 3 electrons or lose 5? Did you learn that electron affinities, which is the energy term for an atom collecting an electron, and ionization energy, which is the energy term for an atom losing an electron, that magnitude-wise electron affinity and ionization energy provided the same oxidation states are under consideration? Magnitude-wise, these energies are equivalent? Did you learn that? This transformation corresponds to the first ionization energy for X. This transformation corresponds to the first electron affinity for X plus. If I measure the energy for this change, how will it compare to the energy for this change? Be the same amount. What will be different? The sign. But the amount's going to be the same. In any case, We're talking here about magnesium being a stronger reducer than zinc. Cited various pieces of information which keep with our recognition that magnesium is a stronger reducer than zinc. And so if you're asked to develop this half reaction, nitrate ion becomes nitrogen, because nitrogen gas is the product that you get when you reduce nitrate ion in 6 molar nitric acid solution with zinc. Well, we looked at nitrate ion converting to NO. We developed a half reaction. What are you going to do to develop this half reaction? How many of these you got to clobber for starts? 2. Otherwise, I don't have enough nitrogen atoms. So when I took and turned nitrate ion into NO, I had to pay attention to -2 oxidation state oxygens going into the pot. That required 4 hydronium ions to eat them up. Here, how many of these -2 oxidation state oxygens are going into the pot? How many? 6. So how many hydronium ions am I going to need to take care of all of these things? How many? 12. That's all you need. That's all you need. Okay. Next. Here's part 4. Part 4 is really a redox system based on complex ion formation. Many metals can be oxidized in strongly basic solution. Not because strongly basic solutions are strong oxidizing systems, but because many metals form stable complexes with hydroxide ion in the presence of water. This is such a case. If you put a strip of aluminum in 6 molar sodium hydroxide solution, you'll see vigorous bubbling immediately as the aluminum begins to disappear. As the aluminum disappears, if you analyze the solution, you'll find out the aluminum containing ion is this thing. So the task is, write the equations for the half reactions. As aluminum is oxidized in 6 molar sodium hydroxide solution, producing this is the aluminum containing ion, and the redox product is a gas. The other redox product is a gas. Well, hey, everything you need to make this ion is in the system. The PSI tells you that. So, 1 mole of this has in its composition mole of aluminum, 2 moles water, 4 moles hydroxide ion. So there it is. That takes care of this half reaction. Just pay attention to PSI. That's all there is to it. Now then, 6 molar sodium hydroxide. Something's getting reduced in this system as aluminum is oxidized to this hydroxide complex ion, hydroxide containing complex ion. So the other redox product, specifically the reduction product, because this hydrated aluminum ion is the oxidation product in this system. The reduction product has got to be derived from 1 or more of these things. That's what's in the system. And when we run the reaction, we see it's a gas. Do you think you're making sodium gas in this system? From a reducing strength standpoint, sodium makes aluminum look like nothing. Do you recognize that beer and soda pop are often sold to you in aluminum cans? You know that, don't you? How'd you like to go get a can of beer with the can being made out of sodium? You want to try that one? That'd be fun. Oh, my beer is in flames. What's going on here? Which of these is the stronger oxidizer? You remember our conversation yesterday? Bad statement. Remember our conversation yesterday about oxidizing systems and their strength and how they depend on pH? The half reaction table shows you that the oxidizing power of a system increases as pH decreases. Which of these then is the better acid? Water, which by default makes it the better oxidizer. Secondly, what do you think the gas is? Because now we've recognized this gas has got to be derived from hydrogen atoms and or oxygen atoms. You're not making oxygen by reduction. You can only make oxygen by oxidation. So we know the gas is hydrogen. Right? And after recognizing water to be a superior oxidizer than hydroxide, that doesn't mean this is a good oxidizer. It only means this is better than that. There's a big difference between making comparisons and making absolute statements. There's a world of difference between saying this guy is strong and this guy is weak versus saying this guy is stronger and this guy is weaker. They might both be gargantuan gorillas, but one weighs 900 pounds and the other one weighs 800 pounds. Big difference in this language. We did this before. As I rip a +1 oxidation state hydrogen from a water molecule, what do I produce? I produce hydroxide ion, don't I? Do I have enough hydrogen atoms in a water molecule to make me a hydrogen molecule? You're damn right, I got 2 of them. But am I getting both of my hydrogen atoms from a single water molecule to make my hydrogen molecule? Because if I take both +1 oxidation state hydrogen from a water molecule, what do I wind up with? Oxide ion. We make an oxide ion in water solution? Not today, not tomorrow, not ever. You've got to put this stuff together, and then it makes sense. So I need 2 of these to make 1 of these, while at the same time I'm making 2 of these. And this multiplier will become 2. I got it over there. But we talked about this so that you would recognize how this half reaction is developed. Now we got a question. As aluminum is oxidized in 6 molar sodium hydroxide solution, with the aluminum becoming this, and water molecules being reduced to hydrogen and hydroxide ion, what happens to system pH during this reaction? Does pH stay the same? Does pH go up? Does the pH come down? What happens to system pH during this reaction?
Stays the same.
I got to vote for stays the same. Anybody willing to second this vote? That's good because the vote's not correct, but at least it was a vote. So it must be true that the pH is either going up or coming down. pH is coming down. That means the system is getting more acidic. That means there must be a net consumption of hydroxide ions in this system, which will be revealed by the net redox reaction. So we look at the half reactions. If I want to couple these half reactions, I got to take this one and multiply it by 3, and this one, by 2, and this one by 3. Watch out, here's the tough part. 2 times 4. 8 moles hydroxide ion consumed. 3 times 2, 6 moles of hydroxide ion being produced. So these half reactions on being coupled tell us that as this reaction runs, there's a net consumption of hydroxide ion, which means the pH is coming down. Hey, you do is a couple of half reactions and you answer the question. All right, let's take a look at parts. Part 5 said, I don't even know why I have this in there. I'm going to get rid of it. Part 5 said, since we're oxidizing aluminum in a water-containing solution, why don't we make hydrated aluminum ion? Come on, hydrated aluminum ion is a pretty good acid. You're not making any acids in 6 molar sodium hydroxide solution. So we go to part 6. Part of the information in the statement of part 6, you're told that hydrogen peroxide is reduced to hydroxide ion. You folks who in laboratory this term get to assignment 10 will run this reaction. You'll use hydrogen peroxide as an oxidizer. Are you familiar with hydrogen peroxide as an oxidizer? You ever use hydrogen peroxide at home? I mean, standard pharmacy strength 3% hydrogen peroxide is common disinfectant. I use it often. You get a cut or an abrasion or something, put a little hydrogen peroxide on it to clean it up. Remember, hydrogen peroxide, good oxidizer, kills the bugs. Acid solutions, pretty good oxidizers, kills the bugs. Acid food keeps a long time. All this stuff fits together if you think about it. So in this case, for part 6, hydrogen peroxide is the oxidizer as it gets reduced to hydroxide ion. Now, for the life of me, I do not know why students are mesmerized by developing from this information the final half equation, the final half reaction. Because one molecule of this has got 2 H atoms and 2 O atoms. So I don't think it's too difficult to recognize this multiplier to establish material balance. Yet I've seen students freeze at this. I don't know why. So there's that half equation. The other half equation is, again, a reaction that you will run in assignment 10 if you get there, and I know a lot of you will in 46L. This is the oxidation. Of this complex ion to this complex ion. I'm not going to bother with the name of this. We got its formula, that's more important than the name. This is called chromate ion, but again, I don't care that much about the name. Formula is far more important. Do you see that this in fact corresponds to an oxidation? Can you look at this formula and tell me the oxidation state of chromium? In this ion, what's the oxidation state of chromium? What is it? Plus 3. The water molecules are 0 oxidation state. Hydroxide ion is a -1 oxidation state species. You got 4 of them. That's 4 minus. But the total charge on the ion is -1. So this has got to be plus 3. Because plus 3 added to -4 gives you the -1. What's the oxidation state for chromium in this stuff? Plus 6. So this is telling us this is an oxidation process. Do you see this formula to be analogous to any other formula that we've just a moment ago looked at? Like that one over there at the top of that board? Your work in laboratory will show you that in many respects, the chemistry of these two ions is quite similar. They're both water complexes of plus 3 oxidation state metals. They're both fairly acidic. They both form these hydroxyl complexes, which are of the same composition. Hey. But back to this. This chemistry is also going in 6 molar sodium hydroxide. I think in laboratory you do it in 2 or 3 molar sodium hydroxide. Doesn't matter. Chemistry is the same. Just for fun. You see this ion? What do you think its shape is? The shape of this ion. Any bets? Mm-hmm. When you looked at forming hydrated aluminum ion, when you looked first at Lewis acid, Lewis base chemistry at the end of chapter 19, do you recall seeing the structure for hydrated aluminum ion in the notes? Did Mr. Mosen talk about this structure with you, at least in brief? Octahedral. Well, this is also octahedral. Not surprising, given that I've got a metal which has interacted with 2 water molecule Lewis bases and 4 hydroxide ion Lewis bases, giving us 6 peripheral species, which is what's required to define an octahedron. Now, everything with 6 peripheral species is an octahedral, but most species are, if they've got 6 peripheral species. All right? Now then, 2 water molecules, 4 hydroxide ions. This is a gee whiz sketch of an octahedron. You know what an octahedron looks like, I think. Okay. Top apex, bottom apex, and then 1, 2, 3, 4 atoms or groups surrounding the thing in the middle in a square arrangement in the equator of this geometric figure. Octahedron, pretty regular geometric figure, even though you have 6 peripheral groups. An octahedron is a simpler geometric structure than a trigonal bipyramid, where you have 5 peripheral groups. Did you learn that in 2045? How many principal angles are there for a trigonal bipyramid? Principal angles for a trigonal bipyramid.
2.
3. What are they? This is a triangle that's perpendicular to the drawing surface. 120, 180, 90. Three different principal angles. 90, 120, 180. Here only two, which is telling you this is a simpler geometric figure. Here to here, here to here, here to here, here to here. Those are all 90-degree angles. And here to here, 180. That's it. All right? Two water molecules. Let's put one of the water molecules there. Now, just for fun. Relative to that water molecule, do you think the second water molecule is here, 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 or here? That's correct. Why? This is a peek at some of the stuff we're going to do in chapter 24. So right now this is for fun. So let's have some fun. Why do you bet the second water molecule is there where it's at a 180-degree angle with respect to the first water molecule, as opposed to being here, 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 or here, where it would be at a 90-degree angle? I'm listening.
Steric hindrance. Steric hindrance.
What does that mean?
Well, it means that the electrons on both.
Electrons?
Yeah, the electron clouds on both the O's, are trying to be as far away from each other as possible because they have, negative charges.
They do?
So that's the furthest away they can.
No, wait. The water molecule has no atoms with charges.
Aren't there partial negatives like on the opposite?
Well, from a dipolar standpoint.
Yes.
Now tell me, what are the other species of which this thing is composed? Hydroxide ions. Do they have charges? Yes. How about that? So take note. The water molecules wind up being in this kind of a position where they're trans to each other because the hydroxide ions want to get as far apart from each other as they can because they have formal minus charges. And the best disposition of the hydroxide ions relative to each other is like this. It would be the same thing if you had a water here and a water here, or a water here and a water here. That's the same as this. The wind blows it, turns the water molecules here or here. More on that in chapter 24. Back to this, because this shows some interesting chemistry. We're trying to convert this thing into this thing, which means I've got to convert oxygen-containing species in this system to oxide ions. From what do you think I'm getting these oxide ions as I synthesize this ion from this ion? This is all happening in sodium hydroxide solution. So my oxygen atom containing components of the system are hydrogen peroxide, that's part of the other half reaction, so we'll rule that one out. Water molecule, hydroxide ion. But all the water molecules and hydroxide ions in this system are not the same, are they? Some of the water molecules and hydroxide ions are floating around in solution. But some of the water molecules and hydroxide ions are chemically connected. The chromium in the +3 oxidation state at the center of this octahedral geometry species. Do you think, when I make this conversion, I'm taking and decomposing water molecules or hydroxide ions which are floating around in solution? Or do you think it's more likely I'm going to decompose water molecules or hydroxide ions which are already connected to chromium. You think that's more likely? They're already connected to chromium. Because when I make this thing, the oxygen-chromium bonds are still there. So I already got oxygen-chromium bonds here. Now then, what groups connected to chromium are being torn apart to make this thing? You think this might involve the water molecules? Or do you think it might instead involve the hydroxide ions? Because if I'm going to turn one of these into oxide ion, how many OH bonds do I have to break?
2.
But if I'm going to turn one of these into oxide ion, how many OH bonds I got to break? And they're all OH bonds, aren't they? Which is cheaper? Breaking one or breaking two?
1.
How about that? So, we can recognize that the water molecules are coming out of this complex. It's going from a 6-coordinate species to a 4-coordinate species. 4-coordinate covalent bonds in this, 6-coordinate covalent bonds here. Now then, as I tear up these hydroxide ions and turn them into oxide ions, what else am I also putting into the system? I'm listening. H plus. In this system, what is assuredly going to catch H plus? Hydroxide ion. Isn't that the best base in the system? So, how many hydroxide ions do I need? And when these hydroxide ions catch the H pluses, I'm making 4 more waters. So now we got a material balanced statement. The remaining puzzle part is charge. 5 moles minus, 2 moles minus. So my electron multiplier is?
3.
And does that not keep with oxidation state change? Because this is chromium plus 3 and this is chromium plus 6. How about that? All fits together. And now if I wanted to, I can multiply the top one by 3 and the bottom one by 2 and add them up and get my net reaction. Okay? Now then. Part 7. Look at part 7 in the notes. Because this is the easiest of all these parts for question 2250. Are you looking at 2250? All we're doing in 2250 is to imagine going to the laboratory, taking some silver nitrate solution, which you have available on the shelf, and dissolving into it some ferrous sulfate, or mixing the silver nitrate solution with ferrous sulfate solution. Did you learn this kind of nomenclature? It's an older nomenclature, but it's still commonly used. It has to do with distinguishing oxidation states. The ick refers to the higher oxidation state, us to the lower oxidation state. You remember the common oxidation state shown by iron in its chemistry? +2 and +3. So this corresponds to iron +2. This corresponds to iron +3. So here's ferrous sulfate. Now, notice that, as it is stated in the notes, we're not only just to look at the redox reaction for this system. As I make this mix, I make silver metal and hydrated ferric ions. I want E0 for the system. Look at the half reaction table. Look at the half reaction table for this system and tell me E0. After you've determined the value for E0, tell me what it is. Bear in mind, on exam 3, a major portion of your work on exam 3 will depend upon your ability to take a half reaction table and put the information to use. What's E0 for this system? I'm listening.
0.03.
0.03 megatons? Volts. Hand up if you don't see where this number comes from. If you're happy with this number, then you're telling me you understand what's going on here. Hydrated iron +2 is getting oxidized to hydrated iron +3, because hydrated iron +2 is the iron-containing species in this solution. As silver ion, AQ is being reduced to silver. So the information you're seeing in the notes shows you this and this.